Hello students, today we are going to learn a new chapter, that is mechanical properties of solids. In this chapter we will be understanding the elastic behavior of solids, then the stress and strain, then we will see the stress strain curve, then elastic moduli which will relate stress and strain for any material. Then we will see the applications of this all knowledge, that is application of elastic behavior of materials, the designing of bridge and etc. And then we will see the torsion of a cylinder or the twisting of wire. So let us begin. First, let us see the elastic behavior of solids. We know that in solid, each atom or molecule is surrounded by the neighboring atom or molecules as shown in figure. Each atom or molecule is surrounded by the other atom or molecules. These are bounded together by an interatomic force or intermolecular forces, and they stay in equilibrium position. All the particles in the nature will always try to be in equilibrium position. When a solid is deformed, the atoms or molecules are displaced from that equilibrium position, causing the change in interatomic distances. For example, we are compressing this object, then the interatomic distance between these two atoms will decrease, and if we are applying the tensile force, then the interatomic distance between these two atoms will increase. The interatomic forces that tend to drive them back to their original position when the external force is removed. Thus, the body regains its original shape and size. The restoring mechanism can be visualized by taking a model of spring ball system. We can understand this as a spring ball system. This interatomic forces are considered to be the spring, and thus atoms are the mass. Whenever spring is compressed or stretched, a potential energy is stored in the spring. So whenever this solid object is deformed, the potential energy is stored in it. In spring, as the spring force acts in the opposite direction of the external force, same way between these two molecules or atoms, the interatomic forces will act to overcome the effect of external force. Now, let us see what is stress and strain. When forces are applied on body in such a way that body is still in static equilibrium, we have applied force but it is not moving, then it is deformed to a small or large extent. Due to the application of this external force, it is deformed to a small or large extent depending on the nature of body and the magnitude of deforming force. When a body is subjected to a deforming force, a restoring force is developed in the body which is equal in magnitude but opposite in direction. This restoring force per unit area is known as stress. For example, let us see this cylindrical structure. The original length is A, original length is L. We have applied some force in this direction, so the interatomic forces between them will act in opposite direction, that is the restoring force. So under the action of these two forces, this body is still in static equilibrium. That means it is not moving. But due to this force, there will be a deformation. So its length is increased from L to L plus delta L. So on the application of external force, the restoring force created per unit area is called stress. The SI unit of stress is Newton per meter square. Now there is another quantity that is called strain. Due to the application of stress, the dimensions of the material are changed. For example, in this case, the length of the material is changed. So strain is defined as the change in dimension upon original dimension. This dimension can be length, area or volume. For example, if we are considering the length, then strain will be change in length upon original length. So in the numerator and denominator both are the units of length. So strain is unitless and dimensionless quantity. Basically, there are three types of stress. The types of stress depends on the point at which force is acting and how force is acting. The first one is tensile and compressive stress. This stress acts along the length. Another one is shear stress. This stress acts along the area. And third one is the bulk stress. It acts as perpendicular to the surface. Regarding this three stress, we will have three deformations, that is three type of strain. One is longitudinal, related to tensile and compressive stress, and thus length will change. Another is shear strain, and thus the elongation or orientation of the object will change. And the third one is bulk strain. It is also called volume strain, because in this case the volume of the object will change. Now let us see stress and strain types one by one, starting with tensile and compressive stress. As the name suggests, it can extend the length or it can compress the object. We have taken one rod of length L and area of cross section A. A force perpendicular to the area is applied on the object. Due to this, there is elongation in the rod that is equal to delta L. Usually, the tensile stress is denoted by sigma, and that is F perpendicular upon A. Remember, here the force should act perpendicular to the area and along the length. The SI unit is Pascal for tensile and compressive stress. As we can elongate the rod, in the same manner we can compress the rod, that is called compressive stress. It is also force acting perpendicular per unit area. In this case, the initial length of the rod was L0 and we have compressed it by the length delta L. So that will be the final length L. Now let us see the strain. Strain is defined as change in dimension upon original dimension. Here length of the rod or material is changing, then strain will be defined as final length minus initial length divided by initial length. That will be L naught. So delta L, that is change in dimension upon original dimension. As this is meter, this is also meter, the quantity will be dimensionless. Let us see one example based on the longitudinal strain and tensile stress and strain. In this example, a rod has a radius of 100 millimeter and a length of 10 centimeter. A 100 Newton force compresses along its length. Calculate the stress developed in the rod. We want to find the stress developed. The stress will be longitudinal stress, that is sigma is equals to F perpendicular upon area. The perpendicular force given is 100 Newton, so that will be 100 divided by area is pi r square. So 100 divided by 3.14. The radius is 100 millimeter, that will be equal to 10 power minus 1 meter. So 10 power minus 2. Simplify this, we will get sigma is equals to 3184.71 Newton per meter square. So this will be our answer. Here, note the very important thing, that whenever a body is under any type of stress, it is in equilibrium, because if we have applied some external force, then to balance it, there is always an equal and opposite force, that is called restoring force, but it will act in opposite direction. So F net on the body will be 0. So it is in equilibrium. Now let us see the second type of stress, that is shear stress. It is also called the tangential stress. There is one object, let us say it is a cube, and we have placed it on the surface. The height of the cube or length of the cube is h. Now we are applying the force along the area, not perpendicular to the area, along the area we are applying some force F. It is called F parallel as it is acting along the area. Now, as this force is not large, this block will not move, but the upper part of the block where we have applied the force will slightly shift in the direction of force. So the upper surface has been displaced by, let's say, x. So we define the shear stress as the force parallel acting tangent to the surface. It is acting along the surface per unit area. So the shear stress is F parallel upon E. Now let us see the shear strain. Here there is not exactly a deformation or change in dimension of the object, but we are just displacing the upper part. Initially it was in this way, and after applying the tangential force it becomes like this. So the upper portion has been displaced by x and height is h. So in this case the ratio of displacement x to the transverse dimensions, that is h, is called shear strain. If we write this angle to be theta, then we can write tan theta is equals to x by h. As x is very small, this x by h will be very small. So for small value of tan theta, we can write tan theta is nearly equal to theta. So the shear strain can also be defined as theta, that is equal to x by h. Now let us see one example based on the shear strain. In this example, there is a brass plate. The height of the plate is 8 cm and the thickness is 0.5 cm. The parallel force is applied in this direction. Due to this, the upper surface is moved by distance x, given x is equals to 0.16 mm. We want to find the shear strain. The shear strain is given by x upon h. X is 0.16 millimeter, so 0.16 into 10 power minus 3 divided by 50. Sorry, it's not 50, it is 0.8 meter. That is 8 into 10 power minus 1 meter. Simplify this, we will get shear strain is equals to 2 into 10 power minus 4. Strain is unitless quantity. Now let us see the third type of stress, that is bulk stress. When a diver plunges deep into the ocean, the water exerts nearly uniform pressure everywhere on his surface and squeezes him to a slightly smaller volume. This is different situation from the tensile and compressive stress and strain we have discussed. This stress is now a uniform pressure on all sides and the resulting deformation is a volume change. So we use the term bulk stress or volume stress and bulk strain or volume strain to describe this kind of quantities. For example, there is a cube of volume V0 and it is kept in air, so initial pressure on the object is P0, that is atmospheric pressure. Now this cube is kept inside a fluid, so fluid will exert force from all the sides and the force exerted will be equal. This will act perpendicular to the surface, so force is acting perpendicular. Under the action of these forces, the cube will be compressed slightly. Let's say after compressing, its volume is V. So the force perpendicular per unit area that the fluid exerts on the surface of an immersed object is called pressure in the fluid. So pressure is defined as F perpendicular upon area. That will be our bulk stress only. The bulk strain is change in dimension upon original dimension. In the case of bulk stress, the volume of the object is changing. It is also a dimensionless quantity. Let us see one example based on that. A spherical ball contracts in volume by 0.05% when subjected to a normal uniform pressure. We want to find the volumetric strain in the spherical ball. The volumetric strain delta V by V will be equal to 0.05 divided by 100. That will be equal to 5 into 10 power minus 4. The volumetric strain is a unitless quantity. When stress and strain are small enough, we often find that two are directly proportional, and we call the proportionality constant as elastic modulus. The harder you pull on something, the more it stretches. The more you squeeze, the more it compresses. So we can express this relation as stress is directly proportional to strain, but this is applicable only when the stress and strain are small enough. So the proportionality constant will be elastic modulus, so we can write stress upon strain is equals to elastic modulus, and this is called Hooke's law. Here note that Hooke's law is not really a general law but an experimental finding that is valid over only a limited range. That is, when stress and strain are small enough, then only Hooke's law is applicable. Now let us see the graphical representation of stress and strain. The Hooke's law, the proportionality of stress and strain in elastic deformations, has a limited range of validity. In the preceding section, we used to phrase such as provided that forces are small enough that Hooke's law is obeyed. Just what are the limitations of Hooke's law? We know that if you pull, squeeze or twist anything hard enough, it will bend or break. Let's look at stress and strain again. Suppose we plot a graph of stress as a function of strain. If Hooke's law is obeyed, the graph is a straight line with a slope equal to the elastic modulus. So the slope of this straight line will give us the elastic modulus. The figure shows a typical stress-strain graph for metal such as copper or soft iron. The strain is shown as a percentage elongation. Here the strain is shown as percentage elongation. The horizontal scale is not uniform beyond the first portion of curve. Up to a strain less than 1%, the first portion is straight line, indicating Hooke's law behavior with stress directly proportional to strain. For line OA, this straight line portion ends at point A. The stress at this point is called the proportional limit. This is called the proportional limit. Up to this point, the stress is directly proportional to strain. Now, from A to B, stress and strain are no longer proportional and Hooke's law is not obeyed. If load is gradually removed starting between O and B, the curve is retraced until the metal returns to original length. So from this point we have started to apply stress. Up to point A, stress and strain are directly proportional. Then further we have increased the stress. Now stress and strain are not directly proportional, but if we remove the stress at point B, then this curve will be retraced. That means when finally the stress is zero, then the object will regain its original shape or original length. The deformation is reversible up to this point and the forces are conservative. That means there is no loss of energy up to point B. The energy put into the material to cause the deformation is recovered when stress is removed. In region OB, we say that material shows elastic behavior. The point B is the end of this region, that is called yield point, and the stress at this point is called elastic limit, because up to point B the object will show or material will show the elastic behavior. Now when we increase the stress beyond B, the strain continue to increasing more rapidly even for small change in stress. For small change in stress, the elongation will move rapidly. But now when we remove the load at some point beyond B, let's say at point C we have removed the stress, then the material does not come back to its original length. From this point, if we start reducing the stress to 0, then this point will be intersect the strain line at the point F, but it is not intersecting at point O. At point O the strain is 0, but at point F the strain is not 0. That means it is not coming back to its original length. Instead, it follows the dotted line, this dotted line. The length at 0 stress now greater than the original length. The material has undergone an irreversible deformation and has acquired a permanent set. Now even after reducing the stress to 0, the original shape is not regained. That is, there is some permanent deformation in the material, that is called permanent set. The point D on the graph is the ultimate tensile strength of material. Beyond this point, additional strain is produced even by a reduced applied load. That means after point D, even if we reduce the stress from D to E, we have reduced the stress, but still strain is increased until point E is reached, at which fracture takes place. That means the material will break down. The behavior of the material from B to E is called plastic deformation from B to E. From O to B it is elastic material, from B to E it is plastic deformation. A plastic deformation is irreversible. When the stress is removed, the material does not return to its original state. For some material, such as the one whose properties are shown in figure, a large amount of plastic deformation takes place between elastic limit and the fracture point. This is elastic limit and this is fracture point. Between these 2 points, there is large amount of deformation, that is strain between B and E is very large. Such kind of material are said to be more ductile because before fracture point or before breaking we can have more and more strain in the material. So this kind of material is more ductile. But if the fracture occurs as soon as after the plastic limit is passed, this is plastic limit, as soon as it is passed, immediately the fracture occurs. That means if the distance between B and E in the graph is very less, then the material is said to be brittle. Soft iron wire that can have considerable permanent stretch without breaking is ductile, while a steel piano string that breaks soon after its elastic limit is reached is brittle. The stress required to fracture the material is called breaking stress. So if we find stress at this point, at fracture point, then this stress will be breaking stress. And it is the property of a material. It depends only on material type. Let us understand what are elastomers. Elastomers are the material like rubber which can be stretched to cause large strains. For small amount of stress, the large amount of strain is produced, then this kind of materials are called elastomers. The best example is rubber. The elastic material, the material which require more stress to produce even small amount of strain. That means in general we have to apply more force to deform it. That means that material is not deformed easily. It's not deformed easily is called elastic material. It is little bit different from our layman meaning of elastic material. In the language of physics, the elastic material means the material which require more amount of stress to deform it or which is not deformed easily is elastic material. For example, steel is more elastic than rubber. We have just seen the stress strain curve. So let us note a very important point, that the area under stress strain curve will give the elastic potential energy per unit volume. It will give energy per unit volume, that is energy density. And the slope of straight line that is the portion where stress is directly proportional to strain. That slope will give us modulus of elasticity. What is modulus of elasticity? That we will see in next lecture.